Hello students, welcome back to another video. In today's video, we'll be doing IGCSE Physics topic sound waves. So first of all, question number 1 is saying figure 5.1 shows a metal strip held to a clamp. This is a clamp on which we have attached a metal strip which is going to vibrate. The end of the strip is pulled down and released so that the strip vibrates. X and Z are the extreme positions of the end of the strips during the vibrations. Y is the mid position. So explain what is meant by the frequency of the vibration. For frequency, let me tell you how does a complete wave look like. So it goes to upper extreme position, then lower extreme position, then again comes to its mean position, and it repeats the procedure: upper extreme position, a lower extreme position, and again come back to its mean position. So this whole cycle is one wave, and frequency is number of vibration or number of waves in a second. Next part is saying the amplitude of vibration of the end of the strip. So amplitude is basically, for example, this is the mean position of the wave, and amplitude is the maximum distance achieved by the wave from its mean position. So in this case, maximum distance is yx and yz. So amplitude of the strip is from y to x or from y to z. Next question is saying figure 5.2 shows two tall buildings A and B that are 99 meters apart. So there are two buildings, building A, which is this side, and building B, which is here, and there is 99 meters of distance between both of the buildings. There is a person who is 33 meters away from building A and 66 meters away from building B. A student stands at P so that the distance from building A is 33 meters. After clapping his hand once, he heard several echoes. The speed of the sound is 330 meter per second. Calculate the time interval between clapping his hands and hearing the first echo. So, what would be the time after which he will hear his first echo? As you know, time is distance divided by speed. He will hear his first echo from the building which is at smaller distance away from him. So sound waves will go from here to building A and from building A to that person. The 33 meter this distance and again 33 meters coming back. So total distance is 66 and the speed is 330 meter per second. So he will hear his first echo after 0.2 seconds. He will hear his second echo when the sound waves will be reflected from building B. And after this, the person will hear his second echo. Time for the second echo would be again the same, the distance over speed of the sound. And the distance covered by the sound would be 66 when going to the building and 66 when returning to the person. So the total distance would be 132. Speed of the sound is 330 meter per second. So after 0.4 second, he'll hear his second echo. So for the third echo, what's the scenario for the third echo? How will this person going to hear his third echo? The formula would be again the same. So for the third echo, the ray will travel from person to building A, then from building A to building B, and then will return back to the person again. So what is the total distance? 33 this side, 99 this side, and again 66 this side. So the total distance traveled by the wave is 198 meter. So I'll divide 198 by 330 again, because 198 is the distance and speed is 330 meter per second, and I will get the answer of 0.6 seconds. So after 0.6 seconds, he will hear his third echo. C part is saying write down an approximate value for the speed of the sound in water. As you know that speed of the sound varies in every medium. In solid, it has the greatest speed, then it has lesser speed in liquids and the least speed in air. So for water, it would be obviously greater than 330 and the value is 1500 meter per second. And you can give any answer between this range. In steel, the value would be even greater than 1500 and it is in range 5000 to 6000. You can write any value within the range. D part is saying figure 5.3 shows a dolphin in water emitting a wave of frequency 95 Hz. Using your value from C, calculate the wavelength of this wave. So the frequency of the waves is 95, and human can only hear within this range, and any frequency that is greater than 20,000 hertz is ultrasounds. So this dolphin is emitting ultrasounds, and that speed of sound in water, I've already told you, is 15 meter per second. So we can just write that in water the speed is this, and to calculate the wavelength we can use the wave equation, which is V equals to F lambda. Arranging it with respect to wavelength, it would be V over frequency. Velocity of sound in water is 1500 meter per second and frequency is 95,000. Dividing them both is 0.016 meters. Question number 2 is saying sound from a loudspeaker is traveling in air towards the solid wall. Figure 7.1 shows a compression of incident sound wave and direction of travel of the wave. And there is a loudspeaker which is generating wave fronts. These are the compressions, and in between them there are reflections. This is wall and sound is traveling in this direction. First question is saying state what is meant by compression. Sound wave is a longitudinal wave. It travels in compressions and reflections. Compression is the area where the air particles are compressed, and then refraction is the area where they are relaxed, then again compressed, and then again relaxed. And in compressions the pressure is high, and in refractions the pressure is low. So what is compression? Compression is basically the point where the particles are closer and the pressure is high. Now, what is this B part saying us? The B part is saying us that the distance from point P to point Q is 8.5 meters. It takes 25 milliseconds for compression at P to reach Q. For this sound wave, determine wavelength. First of all, let us consider what is wavelength. For example, this is a wave. And for sound waves, when wave is going from negative to positive direction, it is refraction. And then when the sound is coming from positive to negative direction, it's compression. Again the same, refraction, compression, and thus continue the pattern. So wavelength is distance between two consecutive refractions, or we can say it is the distance between two consecutive compressions. So coming to the diagram, for example, the distance between two consecutive compressions, this is what we have to find. The question has given us the distance between 5 consecutive compressions. So what we can do is divide 8.5 with 5 and we'll get the distance between only 2 consecutive refractions, which is equals to 1.7 meters. So this is our wavelength. So I am writing it in the area provided. It's 1.7 meters. Now we have to calculate the frequency as well. I have already told you this thing that the frequency is waves per second or number of vibrations per second. In this figure, for example, from refraction to refraction, we have one complete wave. So number of these waves that can travel in 1 second is frequency. We have two formulas to get frequency. One is this wave equation, and the other formula is frequency is reciprocal of time period. Now what is time period? Time period is time taken for one wave to travel. Okay, so from here to here is one wave, and whatever time it will take to travel from any point, that would be our time period. Coming back to this figure, for example, from P to Q, the question have told us that it takes 25 milliseconds for travel. So 25 milliseconds, that we have to convert it into seconds. 25 millisecond would be equal to 0.025 seconds. That means from P to Q, it takes 0.025 seconds to travel. How many waves are there? There are 5 waves. So if we want to get the time taken for one wave to travel, we can simply again divide it by 5. So 5 waves take 0.025 seconds. So what will our one wave take? Divide 0.025 by 5. That would be 0.005 seconds. So time period or time taken by one wave to travel is 0.005 seconds. For frequency, I can take a reciprocal of this value, and this would be equals to 200 hertz. So our frequency is 200 hertz. C part is saying as it strikes the wall, the sound reflects. Complete figure 7.1 to show the position of three compressions of the reflected sound wave. So we have to reflect all the wavefronts, and for reflection the criteria is same. Angle of incidence is equals to angle of reflection. Coming back to the figure and reflecting our wavefronts. For example, you can take any wavefront. So for example, I am just taking this second last wavefront and I am drawing the normal first. Normal is always 90 degree to the plane. So if this is our ray coming to this wall and I have drawn the normal, now I have to check that what is my this wave, like what is the angle of this wave with the normal, and I can see it is making 30 degrees with the normal. So our incident angle is 30 degree. That means our reflected angle from the normal would also be 30 degree. So I am drawing the reflected wave at 30 degree as well. So angle of incidence is 30 degree and the angle of reflection is also 30 degree. Make sure that your direction of travel of wave is always 90 degree to the wavefronts. After making the reflected ray, put on your protector again and make 3 wavefronts again. That would be exactly 90 degree to your direction of travel of your waves. And also make sure that you don't alter the distance between two consecutive wavefronts, because in the reflection the wavelength don't change. So make sure the distance between two lines that are you making should be same as before. Measure it from your scale and make sure that this distance between the lines don't change. D part is saying loudspeaker is immersed in water where it continues to produce sound of the same frequency. So the frequency of the sound is not affected whenever you put it into water. State and explain the wavelength of the sound wave in water compares with the wavelength we have calculated above. So the wavelength above was wavelength in air, and now we have dipped all of this system into water. So what happens to the wavelength now? As you know, in water the speed of sound is greater. So I'm just using wave equation to consider the scenario. So if frequency is same, speed of sound is directly proportional to wavelength, and wavelength is directly proportional to speed of sound. So if speed of sound is greater, that means wavelength will be greater in water than air. Question number 5 is saying figure 7.1 shows the surface of water in tank. So there is a tank in which some wavefronts are traveling towards this barrier, and after this gap they are being spreaded. Straight waves are produced at left hand side and they travel towards the gap barrier, and curved wavefronts travel away from the gap. So this gap is curving our wavefronts. Now, question number 1 is saying name the process that caused the wavefronts to spread out in the gap. What is this procedure? Whenever there are wavefronts approaching any surface which has a gap, it will spread out our waves, and this procedure is known as diffraction. That is spreading of waves around any obstacle. Suggest a cause of reduced spacing of wavefronts to the right side of the barrier. If we only talk about diffraction doesn't affect wavelengths at all. So if the wave is being diffracted, its wavelength is same. That means there is some other reason than diffraction. That could be that there is deep water this side of the gap, and shallow water here. And in deep and shallow water, the frequency of the waves remains same. Frequency this side and this side is same. What changes is speed of the sound. Speed in deep water is greater, and when you see this wave equation, if speed is greater, wavelength is greater. So over deep water we have more velocity or more speed of the waves. That's why we have more wavelength. And in shallow water, the velocity of the waves is lesser. That's why the wavefronts come narrower, because the if speed is less, the wavelength is less. So what is the reason for it? Due to shallow water. Three part is saying state how the pattern of wavefronts to the right of the barrier changes when gap is made narrower. In diffraction, the spreading of waves depends a lot on the gap between the barriers and the wavelength of the waves that are heading towards this gap. Now, how does it depend? For example, if the wavelength of the wave is greater than the gap of the barrier, or the wavelength of the wave is comparable with the gap of the barrier, then the waves would spread very much, or the spreading would be more. You can see it in the picture as well. The circular patterns are very much circular, so that means there is a good spreading. But if the wavelength of the waves is lesser than the gap, or the gap is greater than the wavelength, what happens is that the waves spread like, not spread in the circular pattern, but it would actually spread like this. That means the spreading is very much less. So for this case, the spreading is less. So what's the reason? The question is asking, what if you make the gap narrower? That means the wavelength would be greater than the gap. And for this case, when the wavelength is greater than the gap, the spreading of waves or the diffraction of waves is more. So I am writing more spread of waves. I have attached this worksheet in the description below. You can download it from there. Thanks for watching the video. If the video was helpful, please hit the like button and subscribe my channel.